Welcome to the Adventure to Freedom podcast. Three, two, one. Welcome back to the Adventure to Freedom podcast. Very excited for our guest today, Dr. Geoff Steeves, one of the top 16 candidates in the 2009 Astronaut selection in Canada, and also a physics professor at the University of Victoria.
Yeah, thanks, Mike. Pleasure to be here.
Yeah, welcome. Really happy to have you.
Yeah, thank you.
Let's just jump right into it. So one of the first things I want to talk to you about is just your experience in the astronaut selection. Like, how did you get into that? What made you decide to try it out, and what was involved?
Sure. Yeah. Well, since childhood, basically, one of the dreams was to become an astronaut. And so when I was a kid, I was always kind of thinking about how, what do I actually need to do to make this happen, right? Like what are the steps I need to take to try to be competitive as an astronaut? And it kind of got me thinking about the astronauts and their backgrounds and stuff like that. So one of the things I noticed is a lot of astronauts were pilots, right? And then a lot of astronauts, they also seem to have to be like scientists or engineers or doctors, like medical doctors and stuff like that. So
right.
Yeah, so when I was young, I always loved, pretty much always loved like physics and flying and aviation and kind of the sciencey technical aspect of these things. So so I studied physics in school. Like I really got into it in high school. Like, it wasn't easy, actually. Like it was probably my worst subject in grade 10, right?
So it didn't come like naturally.
It didn't come naturally, didn't make sense, but it was kind of cool because it was like there's a challenge there, right? Like what am I not getting about this, right? So so I kind of kept at it, and I think, yeah.
Did you have a moment where it just started to click for you for physics?
I think so, yeah. Like, I remember like grade 10 physics was not going well. And then I think what was happening is taking math at the same time. And
right.
as the math, as my math kind of got a little stronger, all of a sudden the physics started to make a lot more sense. And,
right.
Eventually it seemed kind of, I don't think it ever seemed easy, but it was at least a lot more doable, and kind of like once your math gets strong enough, you can use the physics equations and you kind of understand what they mean, right? So
right.
Yeah, so it took a while, but I feel like it eventually kind of got there, or it's getting there.
Yeah, the fact that you're a university professor in physics.
Yeah, it's getting better.
Yeah, I hope so.
But yeah, it does take a long time though, for sure.
Yeah, anything worthwhile, I think, always seems to take some time.
Yeah.
So when you, I guess you applied to the astronaut selection, and what was the process there? What sort of happened? How did you know?
Yeah, so basically it was a long time coming. So in 1992 they did a astronaut selection, and so the Canadian Space Agency was looking for astronauts in 1992, and I was like, I still wasn't ready. Like, it was way too soon for me.
I was young at the time.
Yeah, I was alive, but I wasn't old enough. In terms of, like, you had to have at least an undergraduate degree in order to be like considered, but really they wanted you to have much more experience. So basically 92 was like a wake-up call for me. I thought, well, at least they're still looking for astronauts. Maybe they're going to look again. And so that's when I was thinking, okay, well, actually my physics, I was studying physics at university just as an undergraduate, and kind of like opened my eyes up to actually, like with some physics, I could be an astronaut. That's a good background to have, right? And I was sure I wanted to do physics, so that was good. And I actually did some scuba lessons back in, 93 or something like that, right after the recruitment campaign, thinking, okay, if I have some physics and I have some scuba diving, I'll be a better candidate, right? But that was like 92, 93. I didn't realize how long I would have to wait. So
was the next selection, that was 2009?
It started in 2008 and it finished up in 2009. So it was almost like a year-long job interview.
Wow.
So it was a long process. But basically, yeah, from getting that idea in like 92 to 2008-09, it was a long time. But I kept studying physics, and then at some point I kind of had a job. I had a little bit of income, so I was able to start flying. And I think the combination, right, of physics, aviation, a little bit of scuba diving thrown in as well. All three of those things were super helpful because like over 5,000 people applied, right, to be astronauts in that campaign. And so if they're going to pick 2 people out of that group of 5,000, you have to have you have to check a lot of, tick a lot of check boxes.
For sure.
And so that's where the flying physics and all that helped, right? Helped me at least get noticed, right? So the first stage was they opened up the application process, and then 5,000 people applied, kind of thing, and then they had to weed down and find out, who are the 100 people we want to interview, who are the 40 people we want to start doing testing with, and so on, and that's where things got really interesting.
And so, what was the interview process like? And obviously, you made it through the 100 and the 40, and then all the way down to 16, which is very impressive. Yeah,
the interview was weird. They actually did just a video conference interview.
Okay.
Actually, very close to where we are right now. Like for me, they needed to use like a government facility, so the NRC Hertzberg, the center of the universe place.
Right.
Just over here, the observatory. They have a video conference there. So I went up there dressed up in my suit and everything, and went for an interview, and it was interesting. Like they said, we're going to ask you 10 questions, you have 30 minutes, but you have to time yourself, like keep track of what question they're asking you and time yourself in your response so that you don't, like they kind of added that element to the interview, right? So you had to keep track of the whole 30 minutes that you had, keep track of what question they were on to make sure you got through all 10 questions in the allotted time. So they kind of...
Like a time management
management aspect. So you're under intense pressure, you're trying to say the best, give the best responses on every question, but you're also having to keep track of your own time to make sure that you end the interview on time. So it's kind of...
Interesting.
There's a lot of interesting, like, elements, right, where they take something that may be easy and try to kind of make it more complicated, more difficult, more challenging. So the interview I thought went pretty well.
What kind of questions did they ask?
Yeah,
I don't know if you remember.
Pretty big range, right? Some of them were like kind of scenario based, like what would happen if you and your other Canadian astronaut were training to be the first Canadian to like land on the moon or something, and what would you do if they picked the other person over you? Like how would you handle that? Like so it's kind of a little bit different. They talked, imagine you're about to give a press briefing, on a mission, and some reporter asks you like, are you going to bring any mementos up to space? Like what would you say? So kind of a lot of maybe not standard interview questions, much more they want to see just you're reacting to a new question on the spot and to see how you do and whether you had enthusiasm and stuff like that, right? So
interesting.
Yeah, so it was kind
of technical,
not super technical, a little bit of history stuff, like, and you tried to work that in.
But they wanted to know that you knew about
just the basics of it. But the thing about being an astronaut is they want you to be an expert in your own field first, right? They don't expect you to come as a fully trained astronaut. They expect you to be an expert medical doctor, an expert pilot, or an expert scientist.
Able to bring something
bringing that to the equation, and then they're going to teach you how to operate the space station, how to fly the space shuttle, or whatever it is, right? So it is different, right? So it's weird, but I wasn't super knowledgeable about all of space history or operations. I knew a little bit, right? I've learned a lot more since then, but that wasn't really part of the interview. They were more just interested in your accomplishments, your challenges, kind of like who you are as a person.
Interesting.
But yeah, so that was here. That was in the fall of 2008, and then you go back and every day you check your email, right? Because they were corresponding to us from Montreal basically, and so like first thing every morning, just see if you're still in the competition, see if you're still in the competition, and so I got an email in December basically saying keep this week free in January, keep this week free in February, keep this week free in March, right? And you had to work that out with your employer, which was kind of a challenge.
Yeah.
But
I feel like most employers would understand.
Yeah. People are cruel about that. So we got an email in December saying like come to Montreal in January. We're going to start the real interview process, or the real kind of application process, which was where it got really challenging.
And why is that? What was that next
So yeah,
process?
so yeah, we went to Montreal in January, and it was cool because this is, you know, where you actually got to see the competition too, because all of it had been kind of like paper based and just this video intro.
And now is it sort of like group?
Now it was they brought 40 people basically together in Montreal. We went to the Canadian Space Agency headquarters. We went to this military training facility where they do like basic training for the Canadian troops, and they like evaluated our health and fitness. That was like, it wasn't really fun, I would say, because it was like these guys with red shirts who would just yell at you and like make you do push-ups and sit-ups and like run as fast as you can and all this stuff. So
it's almost like a military basic.
It really was. Those were the same people, right? They were yelling at the basic trainees the same way they were yelling at us, except we were all like medical doctors and PhDs and like fighter pilots, but we were like back down to like, you know, Did that really separate the competition? Like, were you able to see like some elements did? Yeah, like I think everybody was mostly in decent shape, like physically. I mean, there's this one guy was like an Olympic athlete. He was doing okay. You know, some of the military guys were in excellent shape.
Were you aware that there was what the...
No, we didn't know what to expect. They wouldn't tell us. I mean, they say bring your gym clothes. Like, they'd say things like that, so it's like, okay, we're going to have to do something.
It's kind of ambiguous, though. You're not really sure what you're getting into.
No, they never kind of gave you... And often our schedules were so funny. It would be like, you're going to do activity 1 from like, you know, 8 a.m. to 10 a.m. Then you're going to do activity 3, right? And it's like, they never told you anything, right, about what they were. But we
just
did
kind of along for the ride.
Yeah. You had to just be able to roll with the punches. And but we did a lot of pool stuff. And that actually, I think, did separate a lot of people out, was you're comfortable, like how comfortable you were in the pool, how comfortable you were underwater.
Right.
There was like a cool puzzle game that, it was kind of like something a child would have. It's like a little, kind of like a little sphere, and on each side there's like a shape for a puzzle piece. And you'd have to like find the, you know, the plus and fit it into the plus shaped holes to go into the inside. But they made us do it like underwater while holding our breath, right? So so you just put a weight belt on and go down to the bottom of the pool, you know, hold your breath and try to do this puzzle. And it's kind of like, I think for people who hadn't done any scuba diving, like they're underwater, maybe they have a fear of water, or maybe they're worried about their weight belt coming off, right? So like that's the sort of thing that I think, you know, the more experience you had underwater, playing around in the pool, scuba diving, stuff like that, you had a real advantage because, you know how to take a weight belt off. It's no big deal, right? So you know you can like focus on the puzzle till the last possible, you know, ounce of breath left, and then you can get up and out. So that was kind of...
Did anybody like get close to drowning with that kind of stuff? So
it's interesting.
I'm sure they have safety.
Yeah, they do, but it's kind of like your instincts kind of kick in. A lot of these activities, though, like they made us almost like we were facing the other way, like which kind of actually creates its own pressure because you're listening. You can just hear
while the other person's
down. Like so many of the competition elements, like they didn't let you see how well anybody else was doing. So like even if you're doing push-ups, or even if you're like doing you know, hanging from a bar or whatever for as long as you can, you know, they would have us in a line facing the opposite direction. They take us one by one to do whatever activity it was. So with the pool it was like that. But we did manage to figure out, like one of the guys, Jeremy Hansen, got every piece into the puzzle, right? And like he actually ended up getting selected. I don't think that was the only reason, but I do remember like he was one who mastered that activity like really well and stuff like that. So it was cool.
That sounds like fun, though.
Yeah, it was fun. I mean, that's the thing. Like, I think if you're the kind of person they're looking for, all of these activities, all these challenges kind of are fun, and they're not scary, right? Like, it's the people who are scared off of these things because of, you know, childhood fears or something like that, or bad experiences, you know, unfortunately they may not be the right people. But not that you shouldn't be scared, but you don't want
if you're going to go to space,
dominate your... you have to be able to work
anything.
through. So it was a great experience in Montreal. We actually got to fly a simulator for the Canadarm, the robotic arm on the space station, Canadarm2, and that was like cool because it was like you felt like you're a real astronaut like at that point. So so it was a good experience in Montreal. But then when we went to Halifax actually the next month, and there were fewer people, right? So
like how many? Do you remember how many?
Yeah, we went from about 40 to about 30 in Halifax.
Wow.
And then from 30 down to about 16.
And is this all so like the fitness and the swimming, the puzzles and that kind of stuff was in like that January week, and then you didn't hear anything back?
Yeah,
and
nope. Check your email every day, first thing in the morning.
Wow.
And actually February they didn't even tell us where we were going. Like they tried to postpone giving us that information because for the people in the military, they have a good awareness of what kind of training facilities there were all around Canada.
Okay.
And
so like they could have an advantage.
They might have
almost?
An advantage, yeah. So they kept it a secret until just a few days beforehand. They told us what week, and eventually we got notification. Okay, you're still in it. So then you do like a quick. By this point, we'd met the other candidates, so you like everybody starts sending emails to one another. I'm still in, and oh, I'm not in, and you got to send kind of condolences to the people who are out, but at the same time, like you're super excited if you're still in.
I guess kind of also figuring out your new competition.
Yeah, like who's still in the running and stuff like that. So and then a few days beforehand they said, okay, book a ticket to Halifax and be here from these days to these days. And that didn't help me any. I mean, I know Halifax, but I didn't know what facilities were there and stuff like that. So, but when we got there, then we found out we had to do the Dunker, which is this helicopter underwater egress training. Yeah, which is really cool. And then we had to do this damage control course, which is it's not directly relevant, I don't think, to working on the space station, but it's equally intense and high pressure to if you had like an emergency on board the space station. So the damage control course was for Navy sailors, where imagine you're in a room about this big, like on a ship. And imagine now the room is flooding, right, with water, or if there's a fire in your ship compartment, or there's a hazardous material spill in your ship compartment.
Did they give you a warning for that, or was it just like out of the blue, like, okay, this is happening right now?
No, it was pretty neat. So they kind of did the damage control course over 2 days. Normally it's like a 2-week course. So on the first day they crammed everything into us in terms of like firefighting, flood control, hazardous material spill control. Like was 1 full day of like theory and here's what you need to do, and then the second day was like all execution. So they're like, suit up, get your firefighting gear on, and we had like full respirators and real fire hoses and stuff like that, and we're going into rooms with like flames coming out of the wall or something like that, and we were using handheld fire extinguishers, but we were also using the hose with 3 people on the hose, and we're like going in like battling fires.
Like
it was crazy, yeah. It was, but there were moments when it was definitely scary too. Like I remember going into one of the days we just started out like firefighting with massive, super intense heat, and they just kept us doing it for a long time, like to kind of wear us down. So it was very tiring. It wasn't dangerous, but like they were making us like move the hose around like really, really vigorously, like fighting this fire. The fire wasn't going anywhere. Like it was, they had the burners like turned up on these like propane burners or whatever we were firing the water at, but they just tried to get us hot and tired. Yeah. And then from there, we walked into a super heated, smoke-filled room. And I've never felt, that's like, I really felt like claustrophobic, because it just felt like you couldn't breathe because your visibility goes to 0. Right. And the heat and everything. And you kind of have to like, okay, I can breathe. But that was almost like the beginning of one of the days. And that was like definitely like a moment for me where I was like, okay, I'm not.
They're not messing around.
Yeah, I was almost feeling like I'm done. I'm done, but what can I do? Well, I can keep walking. Like I was following these other guys into this room, and I was thinking, okay, this is it. I'm too exhausted. I'm not gonna make it. But it was kind of like, we walked through the room, and then we got out into a compartment, and we were doing something else. So it's like, okay, well, I guess I'm not done, right? Because it's kind of like they push you really far, and you just kind of have to think like, is that it? Is this as much as I can do? But it was just like, well, just keep doing your thing, and then it actually got better, right? So it's interesting, but we did a lot of, the flood control was also super hard that day, because it was freezing cold water. This was Nova Scotia in February, and they pumped lake water in as if the room was flooding, because I mean, you know, if your ship is sinking, it's probably not going to be a nice day out, right?
No, yeah.
So it's, you know, freezing cold water, and we were getting like hypothermic, and
wow.
Actually, and again, something that I learned later that Jeremy did is we were working in small teams for this firefighting and flood control, and I wasn't on his team, but for his team, some of the people were getting hypothermic, and he was like pulling them out of the water, letting them kind of like warm up, kind of like he was managing, not only trying to like take care of the situation in terms of the flooding compartment, but he was also not letting his teammates, you know, get into too much trouble, kind of thing. So that was like, again, like the next level, higher level kind of thing, right? But,
managing himself, the situation, and then also the team.
Yeah. So that was really cool. But it was really tough, and that was like a traumatic kind of experience. I would say, like I was kind of shaken afterwards, right? Because it was so intense, right? But
is it almost like, so it sounds like when you went to like the next compartment, almost you weren't sure what.
No, you never knew. You never knew what they were going to do, and then there was one where we had like a hazardous material spill. So basically, you put on your hazmat gear, you go into this room, and it's probably realistic, right? Like there's some people on the ground, like they were dummies, but it's like, okay, there's bodies on the ground. You don't know what has happened, right? So all you know is there's people on the ground. You don't know if they're dead or alive. You don't know if you need to evacuate them or not. You don't know what the spill was. Is it a radioactive thing? Is it a chemical weapon? Is it some other, like a fuel spill? Like you don't know what the situation is. So you're just making it up as you go to some extent, and it was pretty intense. And you know, some of the training, like for you know, chemical weapons, they talk about like, you know, oh, here's a needle, like stick this into your heart, you have like this much time to do it, and you know, anyway, so kind of crazy stuff. Just kind of giving you or getting your gas mask on, like how quickly you have to do that, and yeah, that's crazy.
To see how like they just give you all this information, and then they're almost kind of seeing how much of that you retain, how you can react in a critical emergency.
Yeah, and you're not going to do everything right, but I think they're just wanting to evaluate you under pressure, right? And kind of getting tired. Like it's funny too. Like with well, we learn about like hypoxia and stuff like that in aircraft. You know, if you're up at altitude, but the same thing, kind of like if you're getting really cold and tired, your brain kind of shuts down, it doesn't function as well. So I remember like a moment where there were all these canisters like floating around in this room as the water was filling the room up, and they said, okay, captain needs to know how many canisters of this type there are in the room, and I was like, I don't know how many there are, and there were like 4 of us, and so we're all almost just like standing there, like we can't figure out a way as a group to like answer this request, right? So,
and was there also like a time aspect to these things?
Yeah, wants to know like basically immediately, right?
Wow.
And so that was actually a really good moment for me, because for whatever reason, I was just like, okay, let's figure this out. And I told, like, I just said, okay, everybody, you count in that area, you count this area, you count this area, you count all the ones floating. And I think back on it, and I think like that kind of moment was really critical in getting to the next round, actually, for me personally, right? Because it was just like one of those like little moments where somebody needs to step up.
Right. You took on
and
that
for whatever reason,
role.
I was like, for whatever reason, I felt like, okay, I can do this. It's not like it's the hardest thing in the world, but when you're operating at below capacity, right, because of your coldness and everything like that, but that was really a key moment, I think.
I feel like that aspect of like being a leader as an astronaut, but then also being able to follow instructions as well, like you had to have an interesting balance of that.
Yeah, no, definitely. I think if you're the kind of person who has to be in charge all the time, that's not going to work, right? Because you're working up on the space station, and you have to be able to listen to everybody as well. But yeah, so that was a
sounds like an intense week.
Yeah, it was super intense. It really was, and like not one to be forgotten, that's for sure.
Wow.
And really what was cool too is they didn't always, like, again, like we were working collaboratively then, so at the end of it, like you're not out to get one another and stuff like that. People, this is just like, oh, these are good people you can work with. One of the weird things though was at the end of one of those days, they actually had us evaluate the people we worked with, right?
Interesting.
And that was tough too, because they're like, is there anybody, like, rank the people you worked with, like who was the best, who was the worst, and then is there anybody you'd almost like not want to go to space with, or you know, who would jeopardize your mission, right? And so that's pretty harsh, right? Because it's basically you're saying like, is there one of the people I worked with today whose performance I'm really unhappy with? You know that's gonna like really hurt their chances of becoming an astronaut if you're in that group, right? But apparently this is something they do for real. You know, even when astronauts are training for a real mission, they'll also have this little, you know, checkbox where like if there's somebody who you have real concerns with, you're able to express that. So
that makes sense though as well, to be able to kind of unemotionally, you know, critique and evaluate other people, and knowing that they're also doing the same to you, and trying to do something. Did you have to evaluate yourself on that as well, or was it like where you fit in the team?
No, you didn't. You just ranked the other people, as I recall. I'm pretty sure that was the way it was. But that was a very interesting day, and actually it was only on the bus ride home that we found out about this thing, like that astronauts really did this, and it was actually Canadian astronaut Dave Williams was like riding on the bus with us. He was one of the guys in the back room taking notes on all of us through the process, so we didn't get to know him that well. But just on that bus ride back into Halifax, it was like a blizzard, and I remember it very well. But he gave us a little pep talk that kind of lifted our spirits a little bit, just saying like, you know, that's a very hard thing to do, that evaluation. But it's obviously it's totally
especially after such a for lack of better descriptor, like an emotionally and physically draining day.
Yeah, no, definitely.
Was there any times where you were like constantly being evaluated and you're unsure when, you know, is this part of the test, or are you just asking me this question to get into that?
There's definitely some of that. Like and I mean, it's funny because what we found out was the people evaluating us sometimes like there's the astronauts like ultimately evaluating us and the Canadian Space Agency, but it was the you know, the forces personnel at this damage control course. They sometimes didn't know exactly the rules, like so some of the astronaut candidates were saying, well, can you do this, like like almost like I would ask, you know, like they're kind of pushing the boundaries on what are the rules of like what's allowed and what isn't allowed, you know, for us to ask in terms of requests and stuff like that. And so it was actually causing problems for the examiners, because then they'd have to go ask the astronauts, like, are we allowed to give them this? Are we allowed to, you know? So it was, you know, it was a little bit of improvisation for them too, right?
Yeah.
But
I feel like that'd be a good quality to have, that sort of outside of the box thinking.
Yeah.
But that's, so what you're saying is not always were, like, all the parameters weren't necessarily laid out, like, you can do this, you can't do this, we're expecting this.
I think they had an idea of what we might ask, but then there were some out of the blue questions, right, from some of the candidates, just like, oh, can you know, I would call and get them to turn off the sprinklers, or get them to do this, like maybe that would work, right? And so they had to roll with unexpected requests and stuff like that. So that was kind of neat, but yeah, it was a good experience. The Dunker was interesting too, but and that actually also eliminated some people. Again, I think the people who weren't as comfortable underwater and stuff like that.
Were you doing that as a group? Like, were you egressing? No,
again, one at a time. So basically there was like a little holding area. They'd take us one by one. One person would go, you'd sit in the Dunker, and then there'd be a trainer who would just give every person the same briefing. This is what you have to do. This is you know, how you do it. And then it was like one at a time you'd do it. You were then judged on that one. There was like a one shot? We had it was like 3 different levels. So basically, like, there's like basic Dunker, which is like they're just you're submerged, the cockpit rolls upside down, and you have to get out of your window right next to you. So kind of the simplest way to do it, but you had to use correct technique, and you weren't allowed to start until they gave you the signal to start, basically. So you have to be like sitting there holding your breath upside down underwater, you know, water rushes into your nose, and you just have to like be chill, and then they give you the signal. It's like, okay, get your seatbelt off, open your escape, and get out. But then it, you know, that was like exercise 1. Exercise 2 was you were in the co-pilot seat on the other side of the helicopter. You had to safely make your way across the, you know, the cockpit and then out the other side. And then level 3 was both front exits were blocked, and you had to make your way from the front of the aircraft to the back of the aircraft and get out one of those escape hatches. So
wow.
But I think it was funny. You know, after doing it the first time and finding it wasn't so bad, it gives you this like huge boost of confidence, and then it's like, okay, you know, I can do this. Like, it's no big deal. Right?
Yeah.
But
the pressure of being, you know, just an individual in there, I think is one thing, but I can only imagine, you know, in a real life scenario, you might not be the only person in there and having to deal with other bodies. And
it'd be much more challenging. Definitely. You
gotta kind of help yourself too before helping someone else. But then,
no, it could have been a lot tougher from that point of view, I suppose. But this was still kind of an individual assessment, you know, element. So
that sounds like an intense week.
Yeah, no, it was good, very intense,
more physical.
Yeah, definitely a lot more challenging, and not something. I don't know, I wasn't really prepared for it, right? I think if you were in the military, you'd probably have lots of experiences like that. But for people without that background, it's like you have to like go back to like, you know, whatever crazy stuff you did when you were like a Boy Scout or something like that. Like it's hard to kind of find examples of where you're learning in this.
Did you find throughout this this testing and this training, was there anything that you had like, you know,
I think some of the,
back in the day?
I think some of the aviation actually, like I had done some aviation training, and that was really, really helpful. You know, especially for, you know, the Dunker, for instance, right? Not only is it a cockpit which you're a little bit familiar with, but also just the idea of like an emergency procedure, right? Like you're flying the twin, you have an engine failure, so you have your sequence of steps for controlling the aircraft, identifying what the problem is, verifying, and so on. So kind of like memorizing a checklist, following a checklist through, that was something that I thought aviation training was particularly useful for.
Interesting.
Yeah.
And so after this intense week?
So then it was to Toronto in March. And it was getting into the finals. Like they were looking for 2, and there were 16 of us who went to Toronto. So it was cool, right? Because you're like, you feel like you can see the finish line, but of course everybody's in the same boat. Everybody's hoping they're going to get selected. Chances are good, but they're not really that good.
Did you feel good leaving that like that second week in February? Did you feel good going? Like, did you think that you made it, or were you unsure? Did it give you any hints?
I think I was unsure. Yeah, it was a great experience, right? Like both weeks were amazing. So I really didn't know if I was going to make it or not, and then the last week, so really, you know, super happy to get that invitation to Toronto. It was interesting too, because that's when they released the names of the 16 finalists. So got a little bit famous, right, just for like a day or two. But that was really cool. But the Toronto was mostly medical testing, and there's not much you can do about that stuff, right? Like, you know, you go for your MRI scans, your CT scans, all these different scans, and they just see whatever they see, right? So you just have to, and that's a huge risk, like for the pilots, like the professional pilots in the group. This has happened in the States. People have applied to be astronauts. They've discovered something because they do super intensive medical examinations, and they've discovered things that have disqualified them from flying. Really? Yeah, so you might go in as an F-16 pilot and you come out grounded, right? Like because you wanted to be an astronaut, right? And now you've lost your livelihood, right? So the risks are high, and
it's interesting that they don't do the medical testing.
It's the cost. They did do some. They did do some. Like we went to CFB Esquimalt here.
Like a preliminary medical.
In I think it was November, and they did the emergency diver kind of medical. They did the aviation type medical as well. So like whatever we do on a Cat 1 medical, we did that at CFB Esquimalt, and we also went through like a safety diver, clearance diver medical type exam.
Like preliminary kind of medical screening.
So it's not like, you know, they're going to miss the fact that you've like lost a limb or something like that, but at the same time, they don't, you know, I think it was a cost thing. So when we got into the finals, there's a medical exam to go up on the International Space Station, and this has been agreed upon by doctors all over the world. Is like, here's all the different criteria, here's all the different things that can disqualify you from going up onto the International Space Station, where, you know, if anything happens, you know, any serious medical problem happens, they have to get you back onto Earth, like immediately, right? Right. And they don't want you to die up there.
So, well, also the logistics of then having
was a huge cost and everything.
Too.
Yeah, exactly. So the International Space Station medical is like full on, like everything they can almost think to do, they do. And if you read Chris Hadfield's book, it's one of this almost like the beginning.
Living on.
No, there's another book that he's got just on like his kind of autobiography, I guess. Okay. Maybe it is. Actually, maybe it is the same one. Yeah, he's got many books now.
That's the only one I've read of his.
I think the first chapter starts out with him basically failing his ISS medical as an astronaut, and this was before he was going to command the International Space Station. There was some result that they dug into his past and said, oh, this disqualifies him, but he was already an astronaut, so he fought it and he pushed back really hard. Oh, wow. And eventually he convinced a panel that he should be allowed to fly in the space station. So I
didn't know you could do that.
Yeah, well,
I thought it was just,
I think if you're an astronaut, you got a little bit more credibility, right, in a situation like that, and it really was a kind of a trivial, arbitrary decision that was being made by the medical panel, in his opinion, and he was able to push back. But
it's going to be a pretty smart,
pretty
person to be able to argue that and then be able to persuade them otherwise too.
Yeah. So that was his experience.
Maybe this is all another test.
But it could have been. But so we did the medical in Toronto.
Was there a lot of along with the medical testing for that last week, but there's a lot of like psychological testing?
There was we met with psychiatrists and psychologists from Canada and the US. It was interesting, like NASA was getting involved at this point, so we met with like NASA psychiatrists and stuff like that as well. And we'd filled out like psychological profiles like over the summer, like 2008, summer of 2008, and some other stuff that we did in January, February. And they were like examining it now, like with you there, and they're saying, oh, you said this back in, or how would you answer this question? And then you'd give an answer, and then they'd be like, oh, well, back in August you said this, right? And they were like trying to kind of see that you were giving consistent or even not consistent, like it's like, oh, I'm in a different space now, like they just wanted to see
happen in that
time, exactly, right? Like, or you could just be in a different mind space when you answer a question. Maybe you're thinking about this, but now you're in a different situation, you're being asked the same question, you might give a different answer, and that's okay, right? So they just want to see.
But the face-to-face kind of psychological assessment, I think, would be a lot more intense than when you're filling out this, a questionnaire or something. It's easier to
definitely
maybe not be as authentic, and then when someome's staring you down and questioning you about it, it seems pretty intense.
Do you
remember any questions or like, what the weirdest thing they'd asked you?
There's like some funny things. Like one of the questions was like, this is just a written question. It was like, do you feel like you're always being tested? Which was funny because like if you're in an astronaut selection, pretty much you do, right? Because you just had a week of nonstop testing.
Totally. But I guess that would have been just like a yes/no.
That was just a yes/no.
So that's difficult because then with context comes different answers.
I didn't worry about it too much. I just said yes, right, because of the week we were having. I just thought it was kind of funny, right? So anyway, but anyway.
I guess in life too, Yeah. But I mean, you can kind of test yourself. That sounds intense. Yeah. So that was the.
And then there was and then so. That was, and then actually that week as well, we had a kind of an interesting, it was like a little social gathering, like they had kind of like a wine and cheese thing, but it was not, it was part of the selection process too, in the sense that like, we were being, like, we really met with like heads of the Canadian space industry, right, and companies and stuff like that, and they were like all taking notes on us and talking to us, and some of them were trying to like bait us a little bit even, I would say, like it was tricky as well.
Was anyone trying to like... obviously, there's wine or alcohol. There was someone like trying to get people
drunk, for sure. Like that sort of thing was always in the back of our minds, right? Like even after a long day with the damage control course, you go back to the hotel. Well, the staff who are working for the Canadian Space Agency who are evaluating you are probably like seeing how many beers you're having at the end of the day. Like I mean, like you just gotta be cognizant of that fact, right? Like they're examining you 24/7, and at that wine and cheese, like there was one guy who, like, I don't know if he was doing this for his own personal reasons or not, but I think he was trying to get a rise out of people. Like he was being a little bit antagonistic,
Interesting.
And seeing
one of the examiners or like
just this random guy, right, who was at this event, and we're like, is this an act or is he really like this? And I don't think anybody knows for sure, but
yeah.
the next day we're all like, what was with that guy, right? Like he was being such a jerk, and I think we found out that he was being a jerk to just about everybody.
Probably, yeah.
So you know, this was like his plan. It wasn't like he didn't like me or whatever, right? But wow. He's like, what makes you think your background is going to be in any way useful, like on the space station or something like that? It's like, like you're not used to that really direct, antagonistic, you know.
Especially like in that sort of, you think it's like a relaxed setting.
Yeah, exactly.
Did
so
you
it
know?
Kind of stands out a little bit.
Well, and you're not sure if you are still being tested, or if you're. Like, did you know that was going to be a part of it, or did you heard?
No. Never heard anything like that, right? So it's just. It kind of catches you by surprise. So again, it's just like, okay, you know, falling back on other experiences where you're being scrutinized. I think university, like if you're trying to, you know, work on a PhD or something like that, you have these meetings with your committee and they're going to ask tough questions. So you just have to learn how to try to defend yourself, right, a little bit, right? So that was.
I feel like the wine and cheese event is like it's an interesting social dynamic too, because you're trying to. You know, it's the end of this huge like mountain you've climbed, where you've gotten past all these tests, or you think you have maybe. You almost think, oh, I can relax now. We're out of this, which I think is 100%. You know why they do that.
Yeah, no, that was kind of different.
And definitely, I wouldn't be surprised if that guy was planted there and you told to do that.
Could well be. He's probably like well, yeah, exactly. Could have. Probably was the case. It was an interesting week, right? Because for a lot of us, it was like the end of the process, right? And so we actually, and by this time we got to know each other, right? Like through this really amazing experience. So it was cool. Like we had a little party at the end of the week. We had a couple, like we did, you know, go out, you know, just to a pub locally, like one of the nights. And David Saint Jacques, who's like up in space right now, he brought this flute. That he'd made in Japan, a bamboo flute that he'd learned to play like as a student in Japan, and he played it a little bit and it was like really amazing. So but another guy who wasn't selected actually brought bagpipes into this little pub, but he was actually like an accomplished, he wasn't just like an average guy with a set of bagpipes, he was like an accomplished bagpipe player. And so it was the craziest thing because you have to warm up with the bagpipe. So we're like in a little pub in Toronto. This guy, and we're in a kind of a, you know, a room which had some doors. So we kind of closed the doors, but you can't really warm up a bagpipe without like some heads turning. So he was warming up, and you know, when you're warming up, you don't know if this guy's any good or not. And so we're like. You know,
even sometimes with bagpipes, you're not sure if
exactly.
It's not
an indoor instrument, right? So anyway, so we were like on the verge of getting booted out of the place when he started playing, and then it was like people started buying him drinks and stuff like that because he was really amazing actually. So that was kind of a unique experience. So, but yeah, after it was all said and done, was like. Met such interesting people, so it was almost like, well, how do we keep this going almost a little bit, right? So
a very elite level
and from different sectors or industries and stuff like that too, right? So if you study, you know, physics, you meet nothing but physicists. If you're a pilot, you're mostly just working with other pilots, right? Like that's the kind of person you're working with. And so it was cool to, you know, be kind of like a scientist and then meeting some really cool medical doctors or really cool scientists in different fields, engineers, pilots as well. Like met some like really, you know, these guys would be telling stories about, you know, flying their F-18s and the F-16s. Like these, it's pretty cool stuff actually.
That's crazy. You must have had some good. There's probably some pretty good pub conversations.
Yeah.
For sure.
Oh, definitely. But it was like I had my harrowing stories of like flying Cessna 172s, and these guys are like, oh yeah, I remember when I was like, you know, out of fuel in my F-18. And it's like, oh, okay. Yeah, anyway, so kind of, you can't really compete, right? But it's pretty cool, you know, just to talk to these people, right?
Yeah, well, learn and
elite,
have that other perspective.
Test pilots and fighter pilots and stuff like that. It's pretty amazing.
What, like, when you're applying for the astronaut selection, is there a certain like role you were going for, or did you know?
Really, what it's transformed into now, it changed like over the years. It used to be you had to be basically a test pilot, was like the first breed of astronauts, were almost all test pilots. Because you're flying this super dangerous ship, and you got to have like incredibly fast reaction times and everything else to stay alive. It's changed so much, right? Because nowadays the missions are like typically 6-month missions on the space station. So what you're doing up there, you're taking care of the space station and you're conducting science experiments, right? So it's much more about your ability to be a good scientist and get along with others. So those are the kind of main qualities that you're kind of probably looking for now, or a good medical researcher as well, because a lot of the experiments are medical in nature. Because one of the big things the space station's teaching us now is how can we live in space like long duration, like what do you have to do to keep a human healthy up there. So that's why we're doing these like 6-month studies. We're doing 1-year studies as well, and
be a long time.
Yeah, looking at long term, like what do you have to do to keep healthy, what do you have to do in terms of your blood. Your bones naturally start to lose calcium like almost instantly. As soon as you go up there, your bones start to get thinned out, like osteoporosis. Lose their density? Yeah, because of the type of exercise. So they need to take you know, special medication. They have to do a lot of high impact exercise. It's the
microfractures
impact
and stuff.
Yeah, the impact of your heel on the ground when you're running sends, they call it like a heel shock, and it goes like right up through your skeletal system, and that constant shocking impact strengthens your bones and strengthens your skeletal system, and without that, almost, you know, very quickly your bones start to decalcify and your body starts to kind of deteriorate. And there's all sorts of problems.
Yeah, expanding. Yeah, like don't people get taller because they're
that can happen. It doesn't happen to everybody, but then also the blood distribution in your body. What tends to happen is right away you end up with too much blood kind of in your head without kind of gravity pulling it down, so you end up with too much blood in your head, and eventually what happens is your body reduces your blood volume to kind of compensate for that.
Then getting back down to earth.
So then you get back down to earth, you've got too low blood volume and the blood is going down towards your feet. It's easy for people to pass out really easily when, right when they get back to earth. They got to get their blood volume up again, and so there's lots of challenges, right? And that's what the space station researchers are working on. So like I was an experimental physicist, so I was used to working with all sorts of different types of electronic instruments for taking data and stuff like that. So that's kind of why that's not a bad fit for conducting research on the space station.
And your background was in, let me get this right, ultrafast microscopy?
Yeah, exactly. Yeah, ultrafast microscopy. So
what does that involve?
Yeah, we were building microscopes, but not like optical microscopes that you look through. We were building scanning tunneling microscopes, and what the scanning tunneling microscope does is it's like a super sharp needle, and you just kind of move it over the surface with, you know, a metal surface with atoms, and there's a tiny bit of electricity that can tunnel using quantum mechanical tunneling between the atoms on the surface and the tip of your microscope. So you don't actually, the microscope tip doesn't actually touch the atoms or touch the surface. It just goes within, you know, a fraction of a nanometer of the surface, but it's able to kind of move up and down over the atoms and map them out. So that was a super high resolution microscope that we built those microscopes and developed them. But we wanted to be able to take movies of you know, what was happening on an atomic scale, and it's very fast processes. So we're using flashes of laser light. Actually, we got to build lasers as well, so it's pretty fun.
Always cool.
Yeah, so building these TISAF lasers to develop pulses of laser light, kind of like a strobe effect to kind of not exactly illuminate, but kind of like light up those atoms right when they're a certain part of their motion, and do it over and over again, kind of like, like using the strobe effect to make a fan look as if it's stopped even when it's still spinning. If you light up the fan blades right when the fan is actually at the exact same phase of its motion every time, it makes it look like the fan is stopped even though it's still spinning. We're using the same idea with our microscopes and with pulse lasers.
Like trying to take you know, a video of like a propeller spinning, or even your computer screen sometimes when it, or
exactly. You'll even notice sometimes if you blink and you're looking at a helicopter or something like that, if you blink, your retina retains the image of the helicopter blades frozen, right? So if you just blink, you can kind of see the individual blades. You don't get that blurring out of the motion. So it's not exactly the same thing, but it's kind of a similar effect. Going back to
that for a second, what is quantum mechanic tunneling?
Yeah. So quantum tunneling basically, if you imagine a particle, like this is the way we used to think about, imagine some coffee in a coffee cup, right? In order for the coffee to get out of the coffee cup, the molecules have to have enough energy, right? So if there were like not billiard balls, if there were like marbles in the coffee cup, and you could give the marbles enough energy, suddenly, like by hitting it or knocking it or something, a marble would go flying out of the cup and be outside of it. But if the marbles are stationary, they don't have enough kinetic energy, they can't get out. So if you're stirring up the marbles, maybe you'll give one enough energy, it'll come flying out, but in general they don't have enough energy to come out. Well, with quantum mechanics, if there's like some marbles in here, we have to shrink everything down, so the cup would be really, really small and the marbles would be tiny. But with quantum mechanics, even if a marble that's inside the cup doesn't have enough energy to get out, there's a small probability that it's kind of like it borrows the energy for a short amount of time and then gives it back. So it borrows the energy from the vacuum, it's going to disappear from inside the cup and just instantly appear outside the cup. Even though we could calculate how much energy it had and show that it didn't have enough energy, there's a finite probability that tunneling will occur and it'll just instantly vanish from inside the cup and appear free outside the cup. So it's a crazy kind of concept, but it works. This is the way nature works. There's a specific relationship between how much energy a particle needs to tunnel and the amount of time it can borrow that energy for. If you want to borrow more energy, you have a shorter amount of time to do it, kind of thing. But so there's laws that kind of apply to this, and yeah, that's the kind of a layman's explanation of how tunneling works. So with the microscope, you have a sharp metal tip coming down towards a surface of an atom. The atoms in the metal are trapped in the metal, but if you bring the tip close enough, then there's a chance that it'll spontaneously, an electron will disappear from the metal and appear in the tip of your microscope. The tunneling, the odds of this happening vary with the separation between the atom and the tip. For it to happen, the tip has to be incredibly close to the atom surface, and the probability falls off exponentially as you get further away. So what this means is the tip is very, very sensitive to how far away it is from the atom, and it gives you a sensitive way to kind of image individual atoms. And people have actually used this type of microscope to move atoms around one by one on a surface and build little, rings of atoms and different structures and stuff like that. So,
and that's how I guess that was my next question, is how you can even just set out these individual atoms to
yeah. So normally you just have like you'd get a metal surface out of copper or something, you clean it, and then you just be examining it like just how it was made, like how flat it would be. But people since then have learned how to grow materials like one layer of atoms at a time. So that's kind of a cool technology. But with the scanning tunneling microscope, if you can evaporate a thin layer of atoms on a surface where there's not enough atoms to cover the surface, but just a few atoms scattered about like boulders on a or balls in a gymnasium, like just a few atoms kind of thing on the surface. Then you can use the microscope to kind of nudge these atoms, move them around on the surface and build kind of structures out of them. Yeah, so that was research that was done.
And so when you're doing this, are you adding other variables into this to try to see how things react? And
yeah, you can play around with the temperature, you can play around with the types of atoms, try to figure out which atoms.
Because the temperature would kind of correlate to the amount of energy and stuff.
Yeah, so the amount of energy these individual atoms have is going to be proportional.
The kinetic molecular theory back in high school?
Exactly. Yeah. So if you want if you want these experiments to work, generally you have to cool everything down to super cold temperatures, so the atoms aren't moving anywhere, really, and then you can like push them around. So these experiments are normally done at like 4 Kelvin, so 4 degrees above absolute zero in liquid helium baths and stuff. So incredibly low temperature, because if you heated it up, the atoms would just have too much kinetic energy. They'd start to evaporate and move around and stuff like that. So you couldn't do these kind of experiments at room temperature. I
noticed as well what you said. With back to the quantum tunneling, you said it's a probability that they're gonna instantaneously appear outside of the cup or whatever, which made me think about the classic kind of strange quantum mechanic theory that people often know about, which is the double slit experiment.
Yeah, and that's kind of the classic example of I guess quantum superposition. The idea is that you have a beam of particles, even electrons. This works for electrons, and if you have 2 slits, 2 openings, you shine a single beam of electrons. Some of the electrons will, as the beam kind of expands, some of the electrons will probably go through this slit, some of them will go through this slit, and then what you might expect is a whole bunch of electrons behind one slit and a whole bunch of electrons behind the other.
Right.
Often what you see is actually a whole bunch of electrons in the middle behind both, and it's as if the electrons go through both slits. One electron kind of goes through both slits simultaneously and interferes with itself over at the detector. And this is a real phenomena. It's confusing and strange to people, to the extent that people do this experiment like every year. Like people do this same experiment every year, like with different particles. So people started doing it with photons, with light particles, and it was very strange and confusing. That's how the experiment was originally done by Young, and here we are, like over 100 years later, and still every year there's going to be people doing the same kind of experiment, double slit experiment, but they're doing it with like electrons. They've done it with protons. They've done it with much larger objects now. So C60 molecules, buckyballs. These are carbon molecules that are kind of shaped like soccer balls, made of nothing but carbon. They're still pretty tiny. They're nanometers in size, but they've sent these big, relatively big soccer ball things through an apparatus like this, and they still see interference effects even with these massive buckyballs. So
some of the findings they thought was that it's the observation of the experiment can change the outcome.
Yeah. So I guess in my opinion, so one of the things that people like to do is they like to almost like look at one slit and look at the other slit, and if they see that the electron goes through this slit, or if the electron goes through the other slit, what happens to the interference pattern? And if they observe all the electrons going through one slit or the other slit, you don't get the interference effect. So if you keep track of which slit the electron goes through, then it definitely goes through one slit or the other slit, and you get a pileup of electrons behind each slit. But if you don't look, then you get an interference effect. But what does it mean to look? It means kind of like to interact with the particle, and I think I don't know. In my opinion, it doesn't have to be a human who looks. It just matters whether the electron is interacting in a way that gives away its position. As long as it isn't, it can be kind of going through both simultaneously. But,
almost like Schrodinger's
cat. Yeah, and it's that's another example of superposition, right? The Schrodinger's cat state.
With the double slit experiment and like the particle accelerator, basically, isn't it because there's like a probability matrix, and the only way we can detect where the electrons have fallen, we're actually affecting it using whatever we are using to measure it, like photons.
So you kind of like beforehand you have a probability distribution. So what you're saying is the electron could be anywhere, maybe in this range of positions, and 50% of the probability as it goes through this slit, 50% as it goes through the right slit. As soon as you observe, the electron no longer is in this probability distribution, but you make a measurement and you basically the act of making the measurement, they say it collapses the wave function, and it basically determines, you know, whether it went through this slit or this slit. So if you imagine just flipping a coin, you know, kind of a quantum mechanical coin, and hiding the results, you say, okay, it's actually 50% up and 50% down.
It's heads and tails.
It's heads and tails, and then you open it up and see, oh, it's heads or tails. But in opening up and making that observation, you're collapsing the wave function, and you're some people would even say that you're determining that it's heads or tails, right? By opening up the apparatus and looking. It's the same with the Schrodinger's cat. You know, it's both alive and dead inside the box. You open the box, and if you see a dead cat, well, in opening the box, did you kill the cat?
Right.
Right? Because before you opened it, it was both dead and alive. By opening it and determining that it's dead, have you then killed it, right?
With this double slit experiment, what are they actually using? Like, how would you observe which slit it went into? Like, how would you measure that? Yeah,
you'd have, I mean, it's the same technology that you'd use for your detector. But, I mean, if you have an electron, you know, moving, it's going to generate a magnetic field around it. So maybe you'd have a little sensor sensing if there's an electron moving past because it's generating a magnetic field. You could have a magnetic field sensor or something like that. Yeah, so there's, I mean, you could, what else could you do? You'd have to use some other effect, right? And so there is something called quantum weak quantum measurements, where they try to make a measurement of which slit the electron goes through without, you know, like without destroying the electron or without influencing it. So so this is an area of research that people are looking at. Are there ways that we can kind of, and then there's also this crazy idea that we determine which slit the electron goes through, and then we somehow erase our determination, like going back and going almost like going back in time, and you know, we determined which one it went through, but is there a way that we can kind of like forget that information? And if we forget that information, do we still get a superposition as if it went through both?
And that's the new, not necessarily, that's the quantum eraser concept.
That's kind of the idea, yeah, exactly. And so there are a number of kind of new technologies, like the quantum eraser, kind of quantum random number generator to determine like whether you make a measurement or whether you don't make a measurement. So I can, if I flip a coin under the box, I can open the box and see what the state of the coin is. But can I decide to open the box based on a probability? Like, so half the time I open the box, half the time I don't.
So almost like, so you can open the box if it's heads, but you wouldn't know it's heads unless you already opened the box?
No, not exactly. I think it's more just some of the time you open the box, some of the time you don't, right? And then what does that do to your subsequent measurement? What a lot of papers looking at this research are trying to understand is the concept, one of the concepts is causality, you know, and then the other concept is locality, right? So, so causality is, you know, if I, you know, drop this coffee cup, the coffee will spill, like one, you know, one action leading to a consequence, a definite consequence. Locality is, you know, whether, events happening at different locations can be correlated together, regardless of the space-time interval between them, the distance between them. Like you know, so there are experiments where you take entangled photons, so or you know, entangled particles, and say, okay, this photon has a spin up and this photon has a spin down. We separate them, or actually the photon, one has a spin up, one has a spin down, but you don't know which configuration it is. We just know that they're opposite, and then we separate them, and you make a measurement on one, and that seems to instantly affect the other photon, right?
And this is quantum entanglement.
Yeah, this is quantum entanglement. It is entanglement. The issue, see, what some people believe is that if you have a photon, one is spin up, one is spin down, and you separate them, and you measure one, you find it's up, and the other is down, why should that be surprising? Because one was up and one was down to begin with. We've separated them, we've measured one and found the other to be opposite. There's nothing surprising about that. But what people are trying to understand is, you know, that would be a definite state. You know, the one on the left is up, the one on the right is down. But we can show that that this initial state is in a superposition. So the one on the left is up and down in a 50-50 superposition, and the other one is opposite. Now when we make a measurement on one, it's maybe surprising that the other is instantly the opposite when they're separated by large distances. So maybe they aren't separated. Maybe there's maybe locality is not. Maybe even if we separate things by large distances, there's still a way that those particles are connected.
And when you say instant with this kind of quantum entanglement, was that like, is that faster than the speed of light?
Yes,
technically?
yes. So that's the challenge. Is it is instant. So what I can tell you to do, we can both synchronize watches, and I say, okay, you've got your photon, I've got mine. We're going to go to opposite ends of the solar system, and at 3 o'clock you're going to look at yours, I'm going to look at mine, and then we'll communicate afterwards to see what the results were. So it's a simultaneous experiment being done, you know, across the solar system, or, you know, over some large distance, where it would take hours for a light signal to get from one to the other.
Could we eventually, theoretically, use this quantum entanglement for communication across
and
light years?
I think that's what's really exciting. Doesn't look like it right now. Our understanding is that no information, even though there's a correlation between your photon being up and mine being down, we can't do anything with that correlation until we communicate to one another. Okay. So
up and down part,
because when you make the measurement, you're either seeing up or down. You don't know which one you're going to see. Right. So the only way we could really make it work is if we do some communication afterwards, and that happens at the speed of within the speed of light. So so it seems as if we can't use this for anything interesting. That being said, using superpositions is the fundamental technology of quantum computers, and so these are real computers that people are building. They're very primitive at this point, but it looks as if there are types of computing that can be done much faster if you start with a particle that's both up and down versus a transistor that's either on or off. If you have a particle that's both on and off simultaneously, there are certain types of calculations that can be done much faster with quantum computers. So quantum computing is a real technology being built on these crazy ideas. Quantum communications is another real technology.
Describing that, like the up and down, it reminds me of binary. If you had a 0 or 1, and then if you're able to communicate that almost instantaneously,
it's kind of like if you want to test something out. Well, the analogy, or simple analogy, is imagine like at high school, like there's $1 million behind one of the locker doors, right? And so if, you know, with a classical computer, what you do, or if it was just you trying to find the $1 million, you start opening locker doors one after the other. And on average, if there's 100 lockers, you know, on average you're gonna have to probably open about half of them before you find that one with the $1 million in it, right? So that's a search. With quantum computing, it's almost as if you're like able to open multiple lockers simultaneously, as opposed to having to open them like one at a time. And the way that works with a quantum computer is that it takes about the square root of the number of lockers in terms of guesses. So it's like, if there's 100 lockers, square root of 100 is 10. It's going to take you about 10 guesses to find the $1 million,
opposed to 100,
as opposed to 50, you know, for the classical. So that's fine for 100. But now imagine you have 1 million lockers that you're trying to search through. With a classical computer, you're going to have to open about 500,000 of those doors. With a quantum computer, it's the square root of 1 million, which is 1,000. So now we've gone from 500,000 guesses to get to the answer for 1 million to 1,000. You know, so it scales differently. So it's kind of interesting, right? Like 500,000 guesses versus 1,000 guesses, right? So you can see, as the search becomes more and more difficult, the quantum computer starts to really outperform, because it's able to kind of guess multiple create multiple guesses simultaneously, I guess is a probably oversimplified way to say it.
That's insane though.
But it's neat, right? Because and it's quantum computing is probably where computers were in the 50s, right? Like so like that's how primitive it is effectively. Like it's like, you know, in the 1950s and 60s there were computers, but they were like the size of houses, and they were like full of scientists to run like a computer. You'd have like 50 researchers like working day and night to keep it operating, and that's kind of where the quantum computers are at now.
Do you think this quantum computer could also kind of have a hand in like artificial intelligence one day? Like,
yeah, that's a really good question. I haven't thought about that. Yeah, probably, but you know, it'll probably be like, I don't know, with computers now, like there's the, you know, there's the main CPU, but there's the graphics card, right? And the graphics cards are basically like computers, but they're just like really specialized in rendering 3D graphics. I get this, I don't know, I think right now the quantum computers are going to be almost like a little coprocessor thing, or it's going to be like some part of a general computer system. So for these applications we're going to use the quantum computer, for these applications we're going to use the graphics card, or
we're not all going to have a quantum computer.
I don't think so. Well, certainly not right now, because like again, they're the size of a building. But
what is it that really causes, like, anytime I've heard about quantum physics, aside from my head exploding a little bit, why is it that there's the disconnect between, like, I don't know what you'd call it, Einstein, like relativity and stuff, in the quantum realm, everything seems to just go haywire when you get really small.
Yeah, no, and the thing about quantum theory is that it predicts, it's very accurate, but it doesn't make any sense, right? Like, I think that's the problem that people have. That's why people are, like, it's funny, but I find most people are more interested, in a sense, in quantum physics than relativity, right? Relativity is really cool and really interesting, but in a way it's like, you have the equations, they work, it's fairly, I don't know, it doesn't seem as challenging to understand, whereas quantum physics is perplexing, right? Because it's directly in violation of what we see. Like, you don't see the coffee ever, you know, appear outside this coffee mug, right? Like spontaneously, right? Even though it's allowed by the laws of quantum physics for it to happen on a macro scale, the probability is so low that we never observe it. So I think with that's what's interesting maybe about quantum, is that it really is bizarre. Like, you know, position and momentum are not well defined. So you think of the, you know, ukulele on the wall there, it's in a definite position, it's not moving. In the quantum realm, it's gonna have some uncertainty about its position, it's gonna have some uncertainty about its velocity and momentum. So
even it's depending on your perspective and sphere though too, because I heard about the, not really, more of a thought experiment, but like, even if you bounce a ball or something, it's, when you catch that ball again, depending on which frame of reference you're looking at, so say you're on an airplane and you bounce that ball, it's not in the same place it was, you know, 2 seconds ago, or when you caught it. Even this ukulele, like, we're rotating on Earth, so like, it's also moving, but
there's a lot of
we don't see it.
And some of that is relativistic too, right? Like, if you just talked about bouncing a ball on a plane versus bouncing one in this kind of stationary reference frame here. Now imagine doing it with a beam of light, where you shine a beam of light down onto a mirror and it comes back. That's the same as bouncing a ball, basically, right? But with relativity, you know, the equations actually have to be modified. The definition of, like, momentum has to be changed actually for the light to bounce back, because the speed of light is going to be the same as measured by you on the airplane versus me on the ground watching you go by on the airplane, right? So it's you know, there's some cool physics there with relativity as well. But yeah, with quantum and relativity, they just are in such different domains, I guess, and it's people are looking for ways to kind of connect them, or looking for examples where quantum effects and relativity are both relativistic effects are both going to be at play. So there's something called the, and I don't know too much about this, but it's the black hole firewall paradox. So
they just found the coolest words in the dictionary. Just combine them.
Pretty much. So it's kind of like Hawking came up with this crazy idea that black holes can evaporate. So due to the laws of quantum physics, and this is crazy stuff, but if you have a particle, antiparticle created at the edge of a black hole, there's a chance that one particle will go in and the other particle will escape without violating any of the laws of physics. And if an antimatter particle falls into a black hole and a particle escapes, it's akin to the black hole getting smaller. And so Hawking showed that it looks as if black holes can evaporate. They can actually get smaller as a function of time. But people are now wondering, if you send information into a black hole, does the information ever come out again? Or is it like lost to the universe? And so this is a big challenge because it involves black holes, which are like relativistic. It involves quantum mechanics for black hole evaporation. And now it's actually trying to also involve information theory, because that's something people are trying to understand, is thermodynamics and information. Is information preserved in the universe? Like we think about, like in physics you learn about conservation of energy, conservation of momentum. Maybe information in a sense is also conserved. That's something people are also kind of thinking about, you know, entropy and information. So there's a lot of wild ideas, and but it's really exciting. And these if you read about this firewall paradox, I don't think it's been resolved yet, but it was just concocted a few years ago.
Trying to bridge that
gap. Trying to bridge that gap, finding examples where quantum mechanics is important and relativity is important, you know, to look for cracks in one theory or the other.
Because when you get to, like, the thing that doesn't make sense to me when you get down into quantum mechanics is time seems to be...
Well, and also the direction of time, like just about everything that happens in quantum mechanics will happen if you're going forward in time. You can say, oh, this photon interacted with an atom and it produced an electron and a positron. Okay, so a electron with a positive or with a negative charge and a positron with same mass but negative charge. Okay, so photon, light particle comes in, interacts with the matter, and it produces electron and positron. Well, you can look at that same experiment backwards in time, right? The electron, positron come in, and a photon is emitted. So the same process can happen forward in time or backward in time, and that's like a symmetry. But you know, why does that symmetry exist? That's kind of another question. And does time have meaning? I guess, like when you look at quantum mechanical phenomena, it doesn't seem to. So that's where information kind of comes in. And entropy. Does the disorder of a system, if you look at a big system, it looks as if the disorder of a system stays the same or increases as a function of time, and that's this concept of entropy, and that seems to be one way you can study a system and see whether it's going forward in time or backward in time. If you think about, again, if I drop this coffee cup on your sofa here, you know, I can clearly distinguish which way time is flowing because when you watch the coffee spill and soak, that doesn't happen in reverse, right? So the disorder increases as a function of time, and you can use that if you watch the video analysis, you know, to determine which way time is flowing. Whereas if you look at a billiard ball, imagine just focusing on a cue ball and an 8-ball, okay? And you know, hit the cue ball, so you watch the cue ball come in, hits the 8-ball moves off. If you were to watch that backwards, the 8-ball comes in and the cue ball moves off in the opposite direction. So there's an example of a simple system where you can't tell which way time is flowing. The only reason you'd know is because normally you're trying to shoot the 8-ball into the pocket. But if you just look at the collision between the two balls, it goes one way, it goes the other way. It's symmetrical, right? There's symmetry there.
Wow.
So you can't tell. You can't tell which way time is flowing in that example. Whereas something more complicated, you can clearly tell which way. Like if a plate falls and breaks, you've never seen a plate just reassemble itself, right?
But then if you break down that plate into more of a quantum realm, it's harder to discern which way time is.
No, exactly, right?
That's
so
insane.
if you took, what would be like an object that's going to just break in two, you know, maybe it would be harder to distinguish whether this was like running forward or backward, right? It would have to be a very, very simple object, right? What would be an example, anyway? Like if you imagine whatever, I'm just thinking like two pieces of Lego, right? You know, you can imagine throwing two pieces of Lego together and having them stick, right? You could also imagine, you know, if there was some, you know, something to push them apart, they would just go flying apart if there was like a little bit of energy or something like that. It's not a great example, but like simple systems, right? You see much more. You know, if you can reverse the direction of time and you can't tell which way the process is happening, that typically only happens for kind of simple systems.
What about not necessarily a simple system, but like the CERN, like a particle or the Hadron?
Yeah, Large Hadron Collider. Yeah. So that's
because it's two particles technically.
Yeah, but typically, with the energies associated, you're generating, you know, maybe tens of particles coming out, or hundreds or more. So that's because they're working at such high energies. They're able to like there's, you know.
It complicates that.
It complicates that. So you'd have like 1 million particles created from this collision. You'd never see those particles spontaneously, you know, come together to form. Right. Yeah, so I think there'd be a clear direction there. But in a, you know, maybe more simplistic collisions, you know, it might not be easy to tell which way time was flowing.
That's crazy.
Yeah, there's different, you know. Anyway, there's a number of symmetries it's worth looking into, because symmetries are actually related to, I was just reading about this, I was listening to a podcast about this the other day.
Right on.
Noether's theorem, she was this physicist who discovered that conservation laws, like conservation of energy, is super fundamental in physics. Conservation of momentum is very fundamental in physics. Well, she discovered that these principles, like conservation of energy, are linked to symmetries. So translational invariance is linked to conservation of momentum, meaning if you look at the physics of a system in one reference frame or another moving reference frame, the physics equations are the same, is linked to conservation of momentum. If conservation of energy is actually linked to time reversal symmetry. So there are these symmetries of nature that that are linked to conserved quantities in physics. So it's kind of wild stuff. But again, quantum mechanics is I don't know if it's independent of that or different from that. The other thing about quantum mechanics is often, you know, as you get larger and larger objects, the laws of quantum mechanics seem to be less important, right? You talk about macroscopic systems, but people are trying to build larger and larger objects where they can still see the quantum mechanics properties, and that's really cool, actually. So so try to extend the laws of quantum mechanics into the macroscopic world as much as possible.
To try to bridge those two.
Yeah, bridge those things. Yeah.
One thing I found, I was thinking about the other day. So with larger objects, you know, planets, whatever. You have the effects of gravity. Yeah. What are the effects of gravity on the quantum realm?
And people are actually like looking at that exact question. So that's a brilliant question. So people are basically trying to make large enough quantum objects that they can also see the effect of gravity. The thing about gravity is it's a very weak force. So if you think about it, I'm lifting up this coffee cup. So my arm is stronger than the gravitational attraction of the planet Earth on this coffee cup, right?
Or like magnets and
stuff. So in a sense, like gravity is amazing, like it works over these great distances, but in a sense it's incredibly weak, right? Because, you know, I can overcome the planet's gravitational attraction, right? Just with my arm, right? It's not very strong.
Every time you jump up and
down. Exactly. Like you're overcoming a planet's worth of gravity, so it is a weak force. Because it's weak, it's hard to see how gravity and quantum mechanics interact. So people are trying to look at making quantum objects like bigger and bigger to the point that maybe they can see gravitational effects and look at how those things work together. But people don't I mean, it's a work in progress, right? It's great in a sense. Like, we have these massive theories that are both so successful in their own rights, but we don't understand how they work together.
Because when you go down into that quantum realm, like, are there some, like an individual particle, for instance, like, that's not going to be affected by gravity necessarily?
No, because the other forces are going to be much greater, typically, right? So if you have like one electron, is gravity going to affect it? Well, it is, except for the fact that there's probably a proton somewhere nearby, and the the Coulomb force between those two is so much bigger than gravity that you don't see the effect of gravity, right? The mass of the electron is so tiny, right? And typically there's other forces that are just much stronger. So you'd have to like really isolate that electron with no other particles around to maybe see the effect of gravity on it.
Then I guess, that's the question, is kind of how many particles get to stick together to have that now.
Yeah. So that's
crazy.
That's the thing, is the particles, the mass is so small, the charge is so much higher, right? So, but maybe like a neutron or something like that, where there's like neutral charge, right? Like, that's a particle that is going to have some gravitational force acting on it. It'll be really interesting, to see how gravity, like, does gravity, if gravity is significant, can you still have like a quantum superposition? One of the things people are trying to do is make kind of like diving boards, like at a pool, and if you think about a diving board, you could have it bent down like this, or you could have it kind of bent up like this. They're trying to create a diving board that's simultaneously kind of curved up like this and curved down like this, at the same time, like in a superposition of two curved states, but a simultaneous superposition of both. And how do you even go about making something like that? Well, you can make the diving board. The frequency to create that oscillation, right? But then you have to it has to be really cold, and then you have to somehow, I don't know how you create the initial superposition, or if you just leave it for a while, it'll naturally develop into those two states simultaneously.
That's gonna be insane to see them try to expand this quantum realm with larger and larger objects.
It's a really exciting time. Like, I think there's going to be a lot of technology that comes out of this. Right now, a lot of it is just like fundamental research. People don't know the answers to these questions, but at the same time, like, people are going to figure out ways to make devices out of these technologies that can measure light really sensitively, or can measure acceleration. So, like, I think we're at the beginning again. Like, if you think about, like, where computers were in the 50s, where digital cameras were in the 50s, where iPhones were in the 50s, like, none of that technology, or it was just like, we're just at the edge of that. I feel like we're at the same threshold with quantum technology. Like, it's going from, quantum mechanics used to be, when I was a student, it was all completely theory. Like, these were just thought experiments. This thing about the tunneling and all this stuff, these were just ideas people had, and it was like, you do a calculation, you'd show something, but there was no reality to it. Now people are making lasers based on like quantum transitions. They're called quantum cascade lasers. Like, people are engineering, people are building computers, people are like, starting to put these laws into practice, and so I think we're just at the edge of kind of probably like a new technological revolution. So what would be amazing is if we could learn photosynthesis. Like, how do you just do the super efficient conversion of light into energy that plants are able to do? Maybe we can make much more efficient solar cells with that kind of a technology, right? Even solar cells in general are quantum, but maybe if we can learn a little bit more about photosynthesis, that would have huge applications, right? So,
well, and then even like with the quantum entanglement, and like,
superconductivity is another one, right? Like, transmitting power using high tension lines. There's losses, like you lose energy as you transmit energy over long distances, but with superconductors, there'd be zero energy loss, right? So
would that be like wireless as well? Is that...
no, it'd probably be through a wire, but there'd just be no energy loss. The wire would be a superconducting material. You could make incredibly strong magnets that would, like electromagnets, that you'd never need to Like basically, like when you go for an MRI scan at the hospital, you go into a superconducting magnet. They don't necessarily tell you that. It's a huge magnet,
yeah,
but it's actually a liquid helium cooled magnet. And there's a superconductor inside of it, and there's a huge amount of charge, current, like going around in that superconducting wire, makes an incredibly strong magnetic field. And as long as you keep the magnet cold, the electricity goes around in the magnet forever, and it just creates this permanent like magnet basically with incredible strength. If you let it warm up, it stops working. So that's because superconductors only work at really low temperatures, but people are trying and have been trying for years to find room temperature superconductors that work, you know, at room temperature, at these normal temperatures. So if you had something like that, you could just make like a little electromagnet and charge it up, put some current into it, and then the current would just stay circling around that forever. You could create incredibly powerful magnets and you know, for magnetic levitation for trains and stuff like that. So there's a lot of really cool technologies that hopefully, if we can figure out the laws of physics well enough, we can, you know, engineer these things.
Do you think that, like, bridging large physics and super small physics is going to kind of help to lead this new
I think so.
revolution?
Well, it's one of the questions is, like, do we really need a new, like, maybe our theory of quantum mechanics is good enough. Maybe we don't need to improve on it, right?
Yeah.
Like, because it's getting us a long way. It's just not an intuitive theory. It doesn't make sense to us, but it works, right? So we.
But I guess the issue is to bring these things into, because some of these concepts, if you're able to bring that into, you know, larger realities, like, you know, our kind of dimensions and stuff, like the technological implications could just they sound like sci-fi.
Yeah,
you know?
yeah, and I don't know. Like, it's always hard to. I mean, you can't really predict like what kind of an impact these things are going to have, right? So it's yeah, it's not clear to me. Like a lot of people, like, again, going back to space, it's like a lot of people are really looking for new spacecraft engine technologies, right? Because if we don't get some new technologies, it's always going to take, you know, 6 months to get to Mars, right? Like, there's nothing we can do. Maybe that's the best we've got, right? It's not clear whether those technologies even can exist to get us there, like, way faster or not. Probably fusion is going to be key, but do we need a better understanding of relativity and quantum to get, like, you know, really efficient fusion? Maybe we do, maybe we don't. It's not.
Haven't there been,
it's not
like,
clear yet. I don't
theories
think.
about, correct me if I'm wrong, but like theories of even bending like the fabric of space to go super fast?
Yeah, there are these ideas. I don't know that there's been any proof or any evidence. I mean,
it's all crazy
gravitation.
theories.
Well, the other thing is, maybe even if they're not crazy, we're not there yet in terms of our own, like, level. Like, you know, the strongest magnets people can produce on Earth are maybe hundreds of Teslas, right? Like, half a Tesla is, or 1 Tesla is a really, really strong magnet. If you have 2 super strong magnets, they'll stick together and it'll be hard for you to separate them. Like, you kind of have to pull them apart, and if they snap together and your fingers in between, you can actually, I've heard people breaking their fingers with these super strong magnets if they're large enough. So those are like the strongest, those are like 1 Tesla magnets. We can produce kind of like 100 Tesla magnetic fields on Earth in destructive experiments, where basically we shove a huge amount of current into a electromagnet. The magnet, basically, the wires start to vaporize, the magnet kind of explodes, and in that instant when the current's going through, you get like 150 Tesla or something like that.
Wow.
Like, but like stars, you know, and galaxies produce magnetic fields on the order of like 10,000 Tesla. So we're like at 100. These things are like at 10,000. Like, we got a long way to go, you know, in terms of our ability, like, you know, to mess with energy on these scales, like curving space-time. Like, the kind of energy densities you need for that are so, like, you know, we're not there. We're not anywhere close, right? So, which is cool. Like, you can see, like, in the universe, like, you know, like quasars that put out as much energy, you know, like in a second as our galaxy does. Like, our whole galaxy, you know, like in a year, and you can find quasars that are just like, just throwing out that much energy, like in an instant.
Quasars, for people who don't know, that's a black hole that's also emitting energy?
Yeah. I think it's, how do you get a quasar? Like they're supermassive black holes, and I think I don't know if it's two of them colliding or a supermassive black hole maybe eating a star or something larger than that. So like you've got just matter like flowing into a black hole and accelerating. You know how like if you have a coin going around one of those like
a marble in a bowl,
or something, as it gets closer it goes faster and faster. Well, as a black hole eats a star or something larger, you know, that matter's flowing in faster and faster, and it starts to like radiate a huge amount of energy. And yeah, I'm getting outside of my area of expertise, but it's cool stuff.
Yeah,
right?
there's a lot of crazy parts.
Yeah. So it's cool that you can see that stuff, even if we aren't there yet in terms of what we can do here on Earth. But
I mean, it definitely sounds like you've come a long way from grade 10 to not not really having a firm grasp of physics. And
it's been really fun, but it takes a long time. Like one thing I would say is like I always remembered like going to university and trying to learn physics from my professors, and they seem to know the material so well and at such a high level. And I always thought, you know, if I took a course in the subject, maybe at the end of the course, maybe I'd know the material as well as the professor. And now what I realize, like I've taught courses now, you know, maybe the same course for 5 years. And after 5 years of teaching the course, I feel like, okay, now I'm starting to get it, right? It's about teaching it over and over again, teaching other courses, looking for links between the materials. So some of the concepts do take years. I mean, you know, take years to really understand in a deep way, and you know, and often what a physicist ends up doing with their research is doing the same area of research sometimes for their whole career, and only then, you know, that's how you become a world expert in something, is basically just do that for your whole career, because often these are pretty difficult subjects, and it does take a long time and a lot of analysis to get good, so it doesn't happen overnight, I guess. Yeah.
And what keeps you, you know, what motivated you back then? What keeps you motivated now to kind of be like it sounds like a lifelong learner?
I think that's it. Is I really do like to learn, and you know, it's funny, like if I'm at the university, if I'm teaching the same course maybe for the 5th year, I'm interested in the stuff and so on, but I'm not necessarily learning as much. Whereas if I'm given a new course to teach, you know, and I haven't studied that material before directly, I complain because it's a lot of work. But the fact is, I'm much more interested and excited because you know, the pressure is on. I've got to learn this stuff to try to not necessarily learn it, but like I have to revisit and study this stuff again because I got to teach this new group of students, and I don't know what I'm talking about, so I got to learn this stuff really quick. And that's like really good motivation, and I find that's really I'm happy actually if I'm picking up a new course apart from the extra work, but I'm happy because I get to dive in and try to study the material. And there's different ways you can study it too. Like that's a real benefit too of sticking with it for a long time. Is, you know, when you're a student, you have like one textbook, right? And they're expensive. You know, you've got your one textbook, you paid $200 for it. Over time, you might have, you know, 10 different textbooks on that same topic. And so what's going to happen is when you're struggling because you don't understand it from one textbook, well, you got 9 others that you can look at, and it gives you much better appreciation. Even just seeing how different textbooks teach the same stuff gives you a real advantage, right? So don't give up if you don't understand something. Maybe it's just the teacher you have, or maybe it's just the book that you have as your one book. Like you gotta take a lot of time, but if you really try to learn it, you'll get there, right? It just takes time.
Never give up in that.
Never give up. Never
search
surrender.
for knowledge. Yeah. Well, Geoff, thank you so much for doing this.
Yeah, no, it was a pleasure.
It's been a real pleasure.
Yeah.
We'll let you go.
Okay.
Yeah, right on.
We covered a lot of ground there.